Hello, my name is Draja Brown, and this is my Lab 2 video report. In this lab, I studied the motion of a falling whiteboard eraser in order to understand the effects of net forces on motion. The purpose of this lab was to observe and better understand how gravity and drag forces affect the motion of an object falling vertically. The main guiding physics principle I used was Newton's second law, or equivalently, the momentum principle, as shown here. It demonstrates the relationship between net forces and an object's velocity over time. This principle was then applied to update velocity and position iteratively using these two update formulas. In order to calculate net force, these formulas at the bottom represent the observed forces of gravity due to the Earth and drag force. For this lab, I used Tracker software to analyze the experimental data obtained through the video I recorded, PyThon to create two computational predictive models of the falling motion based on gravity alone and gravity plus drag, and Excel was also utilized in order to compare the results of the data from all three models through the following line graph. The comparison of my observed and predicted data showed that Model 2, which accounts for both gravity and drag forces, is much more accurate than Model 1, which was gravity alone, when compared to the experimental results. For this experiment, the first step in performing this lab was to identify the system and surroundings. My system is a whiteboard eraser that was in our lab classroom, and the surrounding is the Earth. For the experiment, a groupmate of mine dropped the eraser and I recorded its motion. I then used the Tracker software to obtain data about the vertical motion of the eraser. I calibrated distance by using the meter stick we placed against the wall in the video, and I oriented the axes/coordinate system for the y-axis to be parallel with the meter stick, since the video was turned 90 degrees on Tracker. Then I went frame by frame through the video to mark the eraser's position over time. The graphs and chart to the right of this picture were generated on Tracker, and according to the data, my initial y position was slightly larger than 0 due to where I manually marked the origin of the axes. Since the eraser was dropped from rest, the initial velocity was 0. After obtaining this data, I transitioned to Python to create two computational models of the predicted motion of the eraser. Using the start code provided, I input the initial conditions for position and velocity that I just shared, as well as its mass of 0.04 kilograms. I then changed the velocity and position update formulas to reflect what I previously described. I also created a new variable w to represent the force of gravity, which was the vector 0, negative mg, 0 that I stated earlier, and I set w equal to fnet. I followed a similar steps for the second model, except I also created a variable fd to represent the drag force, which was b times the magnitude of velocity squared for the y-coordinate. I had to find the value of b, the proportionality constant, through trial and error by comparing the model's final position results with my observed Tracker final results, and I ended up finding that b is approximately 0.0316. I then set fnet equal to w plus fd, and I ran the code for both models and used their data for my Excel comparisons. Again, here are the results of my experimental data and computational models comparison. Model 1 was less accurate than Model 2, as its object falls quicker than in reality, which is modeled by the blue dotted trajectory. This indicates that another force was acting upon the eraser in reality in order to make it fall slower than gravity alone would cause. Model 2 is an almost perfect prediction, however, of reality, as the yellow and blue trajectories are almost identical. There were still, however, slightly different values between the experiment and Model 2 data towards the middle of the time period, which could be due to human error and me attempting to click the same spot of the eraser at each frame. For the additional questions, what does it mean? Neither of my models explicitly shows the eraser reaching terminal velocity, but Model 2 on the right predicts it. Terminal velocity occurs when the force of drag is equal and opposite to the force of gravity, thus making the net force in the y direction 0, which means that there's a constant velocity and its slope is likewise 0. In Model 2, we don't see the slope of the velocity reach 0 on this velocity versus time graph, but it seems that the curve is leveling out towards it. And what if? Regardless of if the eraser was dropped or thrown down, its terminal velocity would be the same because the force of gravity will always be the same, and therefore the force of drag needed to counteract it would also be constant. However, the thrown object is closer to achieving terminal velocity at the beginning of its motion as the velocity curve flattens out quicker, as we can see in the graph on the right that represents velocity, when the initial velocity does not equal 0, therefore meaning that the object was thrown. So, in conclusion, as demonstrated in this lab, the motion of falling objects is best predicted when taking into account both the force of gravity and drag force, as both exist and play a significant role in the real world. Thank you.